The element curium Cm 96-48 has a mean life of 10 to the power 13 seconds. Its primary decay modes are spontaneous fission and alpha decay, the former with a probability of 8% and the later with a probability of 92%. Each fission releases 200 mega electron volt of energy. The masses involved in the alpha decay are given as follows. We have to calculate the power output from a sample of 10 to the power 20 curium atoms. So we begin by writing the reaction involved in the alpha decay process. So for this problem, the first thing that we are doing is we are writing the reaction involved. So I am writing that the curium 96-248 undergo an alpha decay to convert into plutonium Pu, that is 94-244 plus 2He4. So this is going to be our the reaction that is involved in this particular question. So this is the first thing that we are going to do. The next is this: we are going to calculate the mass defect involved. So we are calculating the mass defect involved, that is delta M for this particular reaction. So this can be written as the mass of reactant minus the mass of product. So over here I am writing it as the value of the mass of reactant is equal to 248.07222 minus the mass of reactant involved, mass of product, sorry. So over here we have product as 244.06100 and minus of helium, that is 4.002603. So this will give us the value of mass defect in AMU. So on solving, we obtain this as equal to 0.00. So we obtain a value of 0.005517U. So this is the value of the mass defect which we obtain. So if we calculate the energy released during the alpha decay, then we can calculate it as, therefore, energy released can be calculated by multiplying it with 931 mega electron volt. So in the question, the value is given to us as 931. So we will multiply this mass defect number with 931 and the value will be obtained in mega electron volt. So on calculating, we obtain this as equal to 5.136 mega electron volt. So next we are moving with the another data which is given to us. So the question is saying that each fission releases 200 mega electron volt of energy. So if each fission is giving us 200 megavolt of energy and the mean life is given to us as 10 to the power 13 second. So now we can say that from the value of mean life, that is equal to 10 to the power 13 second, we will obtain the value of lambda. So disintegration constant lambda is calculated. So the value is T mean is equal to 1 by lambda, and from here we obtain lambda as 10 to the power minus 13 second to the power minus 1. So now the rate of decay at the moment when the number of nucleus is given to us as 10 to the power 20. So over here we are calculating dN by dt, or basically the activity by multiplying lambda into n. So lambda is 10 to the power minus 13 and n is 10 to the power 20. So we obtain 10 to the power 7 disintegration per second. So of these disintegrations, now the problem is saying that there is a probability of 8% and the later is with a probability of 92%. So its primary decay modes are spontaneous fission and the alpha decay that is involved. So I can say the following equation will be holding true for this one. So of these disintegrations, 8% are in the fission and 92% are in the decay. So I can say the energy released per second can be due to 8%, that is 0.08 times of 10 to the power 7 disintegration into 200 uh, value of mega electron volt that is given, plus 92%, that is 0.92 into 10 to the power 7 of the value which we have calculated, that is 5.136. Total value will be in mega electron volt. I hope you understand the value of energy release which I have written. So the question is saying that the energy is released in the two ways, that is during the alpha decay, and then the next one is due to the each fission that is releasing 200 mega electron volt of energy. So it is saying that there is an 8% a chance of fusion reaction and 92% chance of the alpha decay. So we have added the energy in the proportion, that is 8% because of the fusion reaction and 92% because of the alpha decay that is taking place. So on adding we obtain the value is coming out to be equal to 2.074 into 10 to the power 8 mega electron volt. So therefore we can say that the power output in watt will be, power output can be calculated in watt, and this will be equal to the energy released, that is we have calculated as this one 2.074 into 10 to the power 8 mega electron volt. So 10 to the power 6 into 1.6 into 10 to the power minus 19. So the value is in joule per second. So this time we obtain it as equal to 3.32 into 10 to the power minus 5 watt. So with this we have come to an end of this problem. So it is saying that all these things were involved. So there was a probability of 8% of the fusion reaction and the probability of 92% of the alpha decay that was involved. So using this we have obtained the power output in watt as equal to 3.32 into 10 to the power minus 5 watt.